Okay, it should be fine now. Yep. Okay, yeah, I don't know, some weird new Google Meet thing, I suppose. All right, so good morning. Hope you're all able to hear and see me properly. So let's do a quick recap before we start. So in the last class, we were discussing basics of probability. Basically, these tools will be used to prove all our results in information theory. So we started off with the very simple union bound, which says that if you have a bunch of events, then the probability of the union of these events is upper bounded by the sum of the probabilities of the individual events. Right? So that's a very useful tool, particularly when we're trying to find upper bounds on the probability of error of decoding or something of that sort. Right? So, and then we also saw some basic inequalities. We started off with Markov's inequality, which says that if you have a non-negative random variable, then the probability that the random variable takes a value greater than or equal to a is upper bounded by the expectation divided by a. And this holds for any random variable with a finite expectation. Okay, and the Markov's inequality is a very powerful tool, and it helps you prove more powerful inequalities, which are of course specific to other types of random variables. So, for example, by using the Markov's inequality, you can prove Chebyshev's inequality and Chernoff bound. So, Chebyshev inequality says that if a random variable x has finite mean and variance, then the probability that x deviates from the mean by some amount of alpha is less than or equal to the variance of x divided by alpha square. Okay, and in fact, it's Chebyshev's inequality which can be used. It's Markov's inequality which can be used to prove Chernoff bound. So both of these are obtained by applying Markov's inequality to different random variables. So you get the Chebyshev inequality by applying the Markov inequality to the random variable x minus expectation of x the whole square, whereas the Chernoff bound is obtained by applying Markov's inequality to a different random variable, which is e to the t times x. Okay, and so in general, the Chernoff bound is hard to evaluate because what you get is some function of t, and ideally you would want to minimize this over all possible t greater than or equal to 0 to obtain the tightest Chernoff bound. But generally, finding the tightest Chernoff bound is hard. So you can do some simplifications. In particular, if you have IID Bernoulli random variables, then using a number of simplifications, we've also seen these some of these calculations in our information theory course, where I believe it was an assignment problem. So you can show that if x1, x2 up to xn are n IID Bernoulli p random variables, which means that it takes values either 0 or 1. Each xi takes value either 0 or 1, and the probability that xi equal to 1 is equal to p. So if you have n IID Bernoulli p random variables, then the probability that their sum exceeds the mean n times p by an amount in p delta is upper bounded by this quantity over here, which is exponentially decaying. So basically, we'll be interested in such bounds. So whenever we're trying to derive bounds on the probability of error for various kinds of channels or various kinds of sources, we'll use some similar bound. So basically, we'll be interested in getting exponential bounds on the probability of error, and behind this will be some kind of a Chernoff bound. All right, and typically, so we'll make some model. We'll try to identify suitable random variables such that which can be sort of put in the framework of these IID Bernoulli P, and essentially we'll use the Chernoff bound to get an exponentially decaying upper bound on the probability of error. All right, but But there are other concentration inequalities as well, some of which we may not use in this course. But just for extra knowledge, you can just look at these inequalities: the Herfding's inequality and the McDermott's inequality. All right. So any questions regarding the topics we saw in the last class? Any questions? All right, so we also saw different notions of sequences of random variables. We just refreshed what it means for a sequence of random variables to be IID or to be a Markov chain. All right. Okay. So in this class, we'll talk about various notions of convergence of sequences of random variables. So in particular, to understand this, it's good to recall some formal definitions in probability. So in the first course in probability, you would have started off with the following topic. So whenever you're studying a problem in probability, you need to first set down what the notions are. Right, so you start off with the concept of a probability space, which consists of three things. One is the sample space, which is typically denoted by omega, and then on this sample space you have a set of events, the events that you're interested in. What are the outcomes that you're interested in? You may or may not be interested in all outcomes of the event of the sample space. So you have omega, which is a set, and F, which consists of subsets of omega. Of subsets of omega. So in some sense, omega captures what the most elementary or atomic events are, and F consists of all those events which you're actually interested in. And the event space should be what is called a sigma algebra. It should satisfy the following three properties. So the empty set and the sample space should be in the event space. So nothing happening and everything happening should be two events. And if you have an event, then the complement must also be an event. And if you have a bunch of events, even a countable set of events, then their union must be also an event. Okay, and so this is a valid collection of events for a probability space. Now on this probability space, we assign a probability measure, right? And a probability measure is any function which assigns a probability to each event, and in particular, it should satisfy the following properties: that the probability of any event should be always bounded between 0 and 1. The probability of omega the probability of the certain event should be equal to 1. And if you have pairwise disjoint events, then the probability of the union should be equal to the sum of the probabilities. And in particular, this implies that if you have some event A, then the probability of A complement should be 1 minus the probability of A. So again, this is a very quick refresher of very basic probability 101. Okay, and you would also seen the notion of a random variable. So unlike the name that random variable suggests, a random variable is in fact not a variable, it is actually a function. And it is a function which maps the sample space to the set of reals. A random vector maps the sample space to maybe Rn, right? And a random variable is basically any function from omega to R which is what we call measurable. So what this means is that for every open subset of R, basically you can also say that for every open interval, the set of all omega which maps to this interval is a valid event, right? So any mapping from omega to R such that x inverse of any interval a comma b, so this should be a valid event. And in fact, most functions that you can think of are measurable. It is actually very hard to construct functions which are non-measurable. Okay, so this is just a technical definition. It's good to know. But what we're interested in are not just random variables, but sequences of random variables, right? And we want to ask ourselves, what does it mean for a sequence of random variables to converge? We've now understood what it means for a sequence of numbers to converge to something, but when it comes to random variables, things can get very complicated very easily. Okay, so I'll give a series of definitions. So we'll see three different notions of convergence, and in fact these are ordered. So we'll start with the strongest notion of convergence, and we'll go to something weaker, and then go to something even more weaker. So one notion of convergence of sequence of random variables is what is called almost sure convergence, or it's also sometimes called strong convergence or convergence with probability 1. So all these three terms mean the same thing. So we say that a sequence of random variables, x1, x2, x3, and so on, converges almost surely to another random variable x if the following happens. So we say that xn converges almost surely to x if the following thing happens. So the probability that as n tends to infinity, so the limit as n tends to infinity of xn is not equal to x is equal to 0. So let's try to understand this in some detail. So note that each xn, so recall, so that is why it is helpful to think of each xn, each random variable, as a function. So note that a random variable is a function from the sample space to Rn. All right. So it is from the sample space to R, so each xn, right? So basically convergence of random variables essentially corresponds to convergence of functions, right? And if you can understand what it means by functions to converge, then basically you understand what it means when you say that random variables converge, right? And again, when you think about convergence of functions, now you can imagine what can happen, right? So one notion is, so it's after all a sequence of functions. So maybe the sequence of functions converges to some other function, and you want to know what is the probability of the corresponding random variable, right? So although this is what intuitively is happening in almost sure convergence, when you want to check whether a sequence of whenever a sequence of random variables converges almost surely, it is more useful to look at the following definition. We say that a sequence of random variables converges almost surely if for every epsilon and delta greater than 0, you can find some value of m, some integer m, such that the probability that xn deviates from x by an amount greater than epsilon is always less than or equal to delta. Okay, and this happens for all n greater than or equal to m. So for all sufficiently large n, the random variable x must be sufficiently close. The sequence of random variables xn should all be sufficiently close to m. Okay, sorry. Maybe it helps to define it in a little different way. So okay, so maybe I'd like to correct myself a bit. All right. So for every epsilon greater than 0, I can define. Let's do it in the following way. So I'll define this event am. Okay. So sorry, I missed this question by Chandramouli. So for each n, xn is a random variable. All right. So basically, okay. So let's take an example. Okay. So let us take x1, x2, all the way. So it's an infinite sequence of random variables, and each xi is IID Bernoulli half. Right. So each xi takes values either 0 or 1. Okay, and the probability that xi equal to 1 is half, and the probability that xi equal to 0 is also equal to half. Okay. Okay, so in some sense, so each xn is a random variable, which in other words, each xn is a function. Right? So you should think of them more as functions rather than just numbers, because after all, each xn can take different values, and the probability that it takes each of these values could be different. All right. Okay. So, all right. So we want to know what it means for a sequence of random variables to converge almost surely. So let us define the following quantity am, which is that xn minus x is less than or equal to epsilon for all n greater than or equal to m. Okay, so this am is an event. All right, and the event is the following. The event is that there is, so for all n greater than or equal to m, xn minus x is always less than or equal to epsilon. Okay, and we say that xn converges to x almost surely if the probability of am as m tends to infinity, this is equal to 1. Okay. Again, this is a technical definition, so it's best if we see some examples. Okay. So let's start with the following example. So x1 is a uniform random variable. All right, and xn is basically x1 raised to the n. Okay, so xn is x1. So you take a random variable which is uniformly distributed. So it gives you some number, right? Maybe 0.6. So you take, say, 0.6. So then the sequence of random variables, or one realization of the sequence of random variables, would be 0.6, 0.6 square, 0.6 cube, 0.6 raised to the 4, and so on, right? So if x1, so think of x1 as some random number generator, or as the output of a random number generator. So if x1 were equal to, let's say, 0.2, then the sequence of random variables would be 0.2, 0.2 square, 0.2 cube, and so on, right? So basically the entire sequence is determined by x1, right? And essentially all the randomness is in x1. x2, x3, and so on. All right. Is this clear so far? Okay. Okay. So we want to know whether this sequence of random variables converges. So first let us try to guess. Okay. If this sequence of random variables were to converge to something, what would it converge to? Any guesses? Correct. It converges to some real number, but what would it converge to? Correct. So Chandramurli has a good answer. So it converges to 0. All right. Because no matter which number you start off with, so it may be 0.6 or 0.8 or even 0.9999. When you so you have point, so x1 is 0.9999, x2 is 0.9999 squared, and so on. As you keep raising it to the nth power, eventually this will just die down to 0. Okay, so you know that no matter what you start with, it will eventually converge to 0. But it doesn't necessarily mean that the sequence of random variables converges almost surely. Okay, it seems to converge, so let's start with that. But we are not sure if it converges almost surely. So let us look at the definition and see whether this sequence of random variables satisfies this particular definition. Right? So AM is okay. So let's fix an epsilon greater than 0. Okay, let us fix an epsilon and again look at AM. Okay, so AM is the event that xn minus x is less than or equal to epsilon for all n greater than or equal to m. Correct? That is the event. Right? So now that we've fixed, suppose that we fix an epsilon and we fix an m. Okay, so we want to know what is the probability that xn minus mod xn minus x is less than or equal to, or in this case we're guessing that x is equal to 0. Right? So basically what we're saying is that xn is less than or equal to epsilon for all n greater than or equal to m. Correct? So we want to know what is the probability that xn is, so since xn is essentially a monotonically decreasing sequence, so you want to know what is the probability that xm, so the probability of am is basically the same as the probability that xm is less than or equal to epsilon. Correct? So right now we're checking the convergence of the real numbers. We're not checking the convergence of the probabilities. Right? And that is a distinguishing, that is a very important factor. So we're first checking the sequence of the random variables. Essentially, we're checking the convergence of these events. Right? And we'll see that this is different from a slightly weaker notion of just convergence of the probabilities. Okay. So first let's do a couple of examples and then it will be clear as to what is happening and what is missing out. Okay, so what is the probability that xm is less than or equal to epsilon? So is this step clear? That I claim that the probability of am, that is the probability that xn is less than or equal to epsilon for all n greater than or equal to m, is equal to the probability that xm is less than or equal to epsilon. Is that clear? Okay. Okay. All right. So what is the probability that xm is less than or equal to epsilon? So it is a probability that x1 raised to m is less than or equal to epsilon, which is what? No, it's not 1. All right. So for a fixed epsilon and for a fixed m, this is not equal to 1. So note that x1 is a uniform random variable. It's uniformly distributed between 0 and 1. It's a continuous random variable. Yes? Any guesses? So let's try to simplify this. This is equal to the probability that x1 is less than or equal to epsilon raised to 1 over m. Correct? That's easy. Right? Are you sure that it is 1 over epsilon raised to 1 over m? So x1 is a uniform random variable, and you want to know what is the probability that this is less than or equal to epsilon raised to 1 over m. So the probability that x1 1. So m is a fixed quantity, right? So note that m is a number, and so the only randomness over here is in x1. Correct? So let's do a quick recap. So we have a sequence of random variables x1, x2, x3, and so on. Right? I'm defining the following event. The event is what I call am. It's a function of m. It's also a function of epsilon. Right? And the event is that xn is less than or equal to epsilon for all n greater than or equal to m. All right, and I want to find the probability of the event am. Okay, and we've just seen that the probability of the event am is equal to the probability that the random variable x1 is less than or equal to epsilon raised to 1 over m. Right? x1 is a uniform random variable. So what is the probability that x1 is less than or equal to alpha? So it's just what is the probability that a uniform random variable is less than or equal to alpha. Correct, it's equal to alpha, right? So in this case, this is exactly equal to epsilon raised to 1 over m. Correct, right? Yeah, so it's the CDF of alpha, but what is the CDF of a uniform random variable? It's just a straight line with slope 1 from 0 to 1, right? Exactly. So it's alpha. So the probability of AM is equal to epsilon raised to 1 over m. Now what about the limit n tending to infinity probability of AM? So for any epsilon greater than 0, what is this equal to? No. So I'm defining AM for each epsilon, right? So fix an epsilon, okay? And this AM, event AM, is defined for every M. So it is AM, A subscript M, right? And that is the event that all the xn's from M onwards, so basically, so AM corresponds to events on functions xm, x m plus 1, x m plus 2, and so on. All right. So here in this particular example, it is saying that xm plus 1, xm plus 2, and so on, all of them are less than or equal to epsilon. Right? Right. Okay, so in this case, what is the limit as, sorry, so here, I'm not sure if this is what you wanted. So the limit as m tends to infinity of the probability of AM.
One.
Yes, so it's equal to 1, right? It is just limit as m tends to infinity epsilon raised to 1 over m, which is equal to 1. So for every epsilon greater than 0, the probability of the of am tends to 1 as m tends to infinity, right? So this, in this case, so this sequence of random variables converges almost surely to 0. Greater than or equal to 1, so converges almost surely to 0. All right. So let's look at another example. Okay. So suppose now that x1, x2, x3, and so on, it's an IID sequence of random variables. It takes values, so it's a Bernoulli sequence of random variables. Maybe use. So each xi takes values either 0 or 1, and the probability that xn is equal to 1 is 1 over n. Okay. So in this case, so again, we want to know whether this sequence converges almost surely or not. Okay, and again, let's start with a guess. What would this converge to? If it had to converge, what do you think this would converge to? So now you know that xn can take values either 0 or 1. The probability that xn is 0 is 1 minus 1 over n. The probability that xn is equal to 1 is 1 over n. Correct? And you're letting n to tend to infinity. So if the sequence of random variables converges, what do you think this would converge to? Okay. So again, we're not looking at the summation of xn's or anything, right? We're looking at xi. So each xi takes a value either 0 or 1, right? So x1 is either 0 or 1, x2 is either 0 or 1, and so on. So for each xi is either 0 or 1, right? So if it has to converge, it should either converge to some random variable or a deterministic quantity, right? So asymptotically, what is the probability that xn is equal to 1? Right, so the probability that xn is equal to 1 is 1 over n. But for large enough n, this is becoming smaller and smaller and smaller, right? So think about a sequence of random variables in terms of the realizations, right? So you have x1, x2, x3, and so on, right? So what is the probability that x1 is equal to 1? Is 1, right? So n equal to 1. So the first one is always a 1. The second x2 is a random variable with, so half probability half it's 0, probability half it is a 1. So maybe one realization of this is that it's a 0. x3 is 1 with probability 1/3. So maybe it's a 1. And then x4 is 1 with probability 1/4, 0 with probability 3/4. So maybe it's a 0, then you have 1, 0, 0, 0, 1, 0, and so on, right? So basically, you're tossing coins, right? But you're not tossing the same coin multiple times. Okay, you're essentially you're tossing biased coins every time, and the bias is becoming more and more towards heads as you keep on tossing. Correct. So this is one possible realization, and this is another possible realization, and so on. But eventually, for large enough n, what do you expect? Do you expect to see more zeros or more ones for large enough n? Yeah, so expect to see more zeros, right? Because the probability that xn equal to 0 becomes more and more likely as you go on. Right? So, but now, so if this had to converge, we could guess that if it ever had to converge, then it would converge to 0. X equal to 0 with probability 1. So this is the random variable that it would converge to if it converged almost surely. So once again, let's do the above exercise for this sequence. All right, so you fix an epsilon greater than 0, and you define am, the event am, as the event that xn is less than or equal to epsilon for all n greater than or equal to m. Okay, so in this case, it is the probability that, yeah, so now we can't do any simplifications. So the probability of am is the probability that xm is less than or equal to epsilon, xm plus 1 is less than or equal to epsilon, and so on, right? It consists of infinitely many random variables. Okay, so this okay, and we want to know what is the probability of this particular thing happening, right? Any questions so far? So we want to know what is the probability that beyond a certain point, beyond m, So you have the sequence of random variables. Okay, you fix a particular point, say this particular location. I want to know what is the probability that after this point, everything to the right of this is all less than or equal to epsilon, right? So basically I have a random sequence and there can be different realizations, right? So this is one realization, this is another realization, and I could have a third realization. There are infinitely many realizations, right? But what I want to know is, suppose that I fix this particular location, what is the probability that after this, everything, what is the probability that to the right of this location, all these numbers are going to be less than or equal to epsilon? Right? Exactly. So as Chandramouli rightly points out, this is the probability that to the right of the location that I'm interested in, I see only zeros. So it is a probability that xm is 0, xm plus 1 is 0, and so on. Okay? And basically I want to find a bound on this probability. Okay? So just to simplify, let me try to get an upper bound on this. So this is less than or equal to the probability that xm equal to 0, xm plus 1 equal to 0, and I fix some capital N. Okay, so everything between m and capital N, everything is 0. Okay, so why is this an upper bound? Or is it correct? Is it really an upper bound? It's equal. Why do you say it's equal? There's no dependence, but for example, compare this.
So probable, I mean, we are considering all zero scenarios. So if one comes, then I think that would be less than this value.
Correct. So the important point here is that, all right. So let's look at the two events that we're interested in. Okay. So I have this event AM, which is the event that xm is 0, xm plus 1 is 0, and basically everything beyond xm is 0. Now I'm defining another event. Let me call it am comma n, that xm is 0, xm plus 1 is 0, and up to only xn. Okay, I don't care what happens beyond xn. Okay, what can you say about these two events? Correct, right? So am contains am comma n. Am comma n contains am, so therefore the probability that of am comma n should be less than or equal to wait, so are you sure that this is so are you sure that this event contains this? So if am happens, you know that am comma n happens for sure. But if am comma n happens, are you sure that am will happen? So AM is a subset of AM comma N. So the probability of AM comma N will only be greater than or equal to the probability of AM. Right? All right. Now that we have that, so what is the probability of AM comma N? So you know that xm plus 1 up to xn are all IID random variables. So what is the probability that this happens? What is the probability that xm equal to 0? It is 1 minus 1 over m, correct? And what is the probability that xm plus 1 is 0? It is 1 minus 1 over m plus 1, so on, up to 1 minus 1 over m. That's correct. So let's try to simplify. So what is this? It is m minus 1 over m. What is the second term going to be equal to? Yeah, so right, so Sohit Kumar actually has the final answer, but anyway, this is m over m plus 1. You'll get m plus 1 over m plus 2, so on, all the way up to n minus 1 over n. So this will be something, a telescopic quantity, so you can cancel these, and eventually what you will get is just m minus 1 over n. Right? So am comma n is basically m minus 1 over n. Right? And you know that, but what we are interested in is am. So the probability of am is less than or equal to the probability of am comma n. This is true for all n. So in particular, this is true for the limit as n tends to infinity of the probability of am comma n. But what is this equal to? So you fix an m and you're letting n to tend to infinity. Right? So this is simply equal to 0. Right? So this is equal to 0. So the probability of am is equal to 0 for all m. And therefore it does not satisfy this property over here, that the limit as m tends to infinity, probability of am equal to 1. Okay, so let's try to see what is happening. We saw two different examples. In the first example, the sequence converged almost surely, whereas in this example we see that it's somewhat converging. Eventually you will of course see more zeros than ones, but you can't say for sure that you will never see a 1 beyond a certain point, right? So in this case, you're almost certain that beyond a certain point, you're not going to see anything more than epsilon, right? It's going to be very close to 0. But in this particular example, it is a small probability, but eventually you will encounter many ones. So it will happen very infrequently, but for sure, you will see some ends, you will see some ones beyond a certain point, right? Irrespective of which point you choose, beyond that, there will actually be infinitely many ones. They'll be very, very far apart, but there will be ones for sure. So that is why this sequence does not converge almost surely to zero. Right? Any questions? All right. So there's a third example which I want you to try and work out on your own. Right. So you again have a sequence of random variables which are IID, but each random variable is uniformly distributed between in the interval 0 to 1 plus 1 over n. So eventually, what do you think this will converge to? If it had to converge, what would it converge to? What does it look like eventually? As n tends to infinity, what happens? Correct. So check if this converges to the uniform 0, 1 random variable. So your goal will be to check if the sequence of random variables converges almost surely to the uniform 0, 1 random variable. All right. So I leave that to you as an exercise. So now let's explore a slightly weaker form of convergence, and it is convergence in probability. So we'll say that, so previously the convergence was actually in terms of the random variable itself, but now the convergence will be in terms of the probability. Okay, so we want to know if these probabilities converge. It is not exactly in terms of the probabilities, we'll see a weaker notion later on, but we say that a sequence of random variables converges if the probability that xn minus x is greater than epsilon, if this sequence of probabilities converges to zero. So this is different from almost sure convergence, where we said that, where we wanted that the probability that the limit as n tends to infinity xn minus x, the probability that this quantity was greater than epsilon should be equal to 0, right? So in this case, the limit is within the probability, whereas here it is outside the probability, and it makes a very big difference. Okay, so let's see again. Let's see these two examples. So again, we look at these three examples and find out whether they converge in probability or not. So I leave it to you as an exercise and to show that the first case, it also converges in probability. Converges in probability to x. Okay, but let's see the second example. So here xn is basically IID Bernoulli 1 over n, right? So each xi is IID Bernoulli 1 over I, and we saw that this does not converge. So this does not converge almost surely to 0. So let's see if xn converges almost surely, converges in probability to 0. Okay, so in order to do that, we just need to find what is the probability of this happening. So what is the probability that xn minus 0 is greater than epsilon? All right, So for any epsilon greater than 0, what is this equal to? Remember that each xi is IID Bernoulli 1 over n. So for Bernoulli random variables, what is this probability equal to? The probability that xn, so the probability that xn is greater than epsilon. Yes? So what values can xn take? Now xn can take values either 0 or 1, right? So it's a sequence of Bernoulli random variables, right? So xn is either 0 or 1, correct? So xn can be greater than epsilon only if xn equal to 1. Right? So this is a probability that xn is equal to 1. But what is this probability equal to? It's equal to 1 over n, right? Because xn is IID Bernoulli 1 over n. Right? So, but as n tends to infinity, this tends to 0. So the probability, this limit as n tends to infinity, xn minus 0 greater than epsilon, this is equal to 0. Therefore, xn converges in probability to the number 0. All right? So similarly, try to work out the third case, the third example. All right. So what happens if each xn is IID but uniformly distributed in 0 to 1 plus 1 over n? Right? Okay. So we'll continue in the next class. But if you have any questions, you can ask them now.